Thank you all for being here. I'd like to thank the sponsors and the organizers. And so I work for USGS, as you just heard, and comes under the Department of Interior. The first time I've ever been in this room. It's a cool room. I like this big golden eagle over my head. So I'm going to talk about the raster side of the table. You just heard about through OpenStreetMap, the vector side. I've worked both sides of that table. I used to work for NGA for a number of years. I've been with USGS now for maybe about 7. And I'm the acting director for EROS. That's the Earth Resources Observation and Science Center. In Greek mythology, Eros is known as the god of love and desire, so no connection to Eros. So I'm going to talk about what I'm calling open land imaging for data science. I hope you won't hold it against me for using data science in there. It's the buzzword du jour. Everybody uses it along with AIML. I'll have a few choice words to say about it in a good way in my talk here. But I'd like to commend the open source community for what they've done. So Yogi Berra said that when you get to the fork in the road, take it. And that's what this community has done. They've taken that proverbial fork in the road and they've stuck it in the traditional software acquisition model. And so hats off to this community for doing that. Next slide, please. So EROS is located in Sioux Falls, not Fall. Sioux Falls, South Dakota. The doors opened in 1973. The reason it's in the middle of the country there, it's actually in the middle of corn and soybean crops, and I'm not from there originally. I've been there for the past few years. Was back in the early 70s, this was the site this site was decided to be the ground station, if you will, for the Landsat mission. Landsat 1 launched in 1972. And at that time, we didn't have, big dish antennas all over the planet like we do today. So it was very strategic geographically to have this in the center of the country to ensure maximum coverage for, overpasses and reception. And that's where, of course, it's been ever since. Next. Here you see the founders in effect, they're the founders, you might say, of EROS, DOI Secretary Stuart Udall, who this building is named in honor of, and then USGS Director William Pecora, back in the mid-60s, made a bold proclamation about having a federal civil Earth observing satellite, and it touched off a firestorm. They didn't give any heads up to the administration at the time, the Johnson administration. Touched off a political firestorm. NASA, the DOD, everybody was up in arms that these two gentlemen had the audacity to put out this press release without notifying them. And so EROS originally stood for Earth Resources Observation Satellite. That was going to be the acronym for the first satellite, which later became Landsat 1. But the acronym was repurposed for what has become the center, right? So the S used to stand for science, now it stands for satellite. So, but this was some pretty significant risk-taking back in the mid-60s that these two gentlemen did. Pecora later is known to have said to his wife that he thought he was going to get fired as a result. And rumor has it that Lyndon Johnson never spoke to Stuart Udall after this episode. But this was some serious risk-taking that, we don't necessarily see as much anymore. But that's taking some risk. Next, please. So here is a timeline of the Landsat series of satellites going back to 1972. You can see we're up to Landsat 9 now, just recently launched about a year ago, in September of last year. We still have Landsat 7, 8 operating. 9 was essentially a copy of 8, and I'll show you some of those particulars later. So what's on the I guess the drawing board, if you will, for Landsat Next has been advertised through various requests for information in terms of what the users are looking for. So the spectral and the spatial and temporal resolution will most likely go up or increase for Landsat Next, which will probably become Landsat 10. You can see our 50th anniversary logo there. So, you know, Landsat, it's an amazing story that Landsat still exists after 50 years. I mean, how many government programs can say that? It's practically become, I mean, it's an iconic name in the remote sensing community, right? Right up there with Nike and Coca-Cola. It's got that brand recognition, and many folks who started or spent some part of their career dealing with raster data and satellite data cut their teeth with Landsat, right? And it wasn't until 2008 that it became free and open. It was considered a public good, which really changed the landscape for how Landsat gets used, especially the archive. Next, please. So we've done formal valuation studies over the past decade, and you can see in that graphic on the left, to try to get a sense of what the valuation is, you know, in terms of US dollars of the Landsat data. And you can see that top graphic, you know, in 2011, the top part of the left graphic, in 2011, it was valued at just over $2 billion, and then in 2017 at $3.5 billion. Now, the methods we used to do that valuation study were entirely based on download rates from, at that time, was mainly from our on-prem, you know, servers at Aeros. That's changed. The Landsat archive is now in an Amazon Web Services cloud. The users don't know the difference. You know, you go through the usual GUI to get to it. But it also means that the way users interact with the data has changed and will continue to, where we'll see less downloading and more doing your analysis in the cloud. Of course, that's good for the cloud providers, but really we have to look at the way we do interact with large amounts of data going forward and change the way we think of how we do our analysis, right? It's a pretty big, you know, shift, but we're kind of seeing that go on. So the bottom graphic shows you that graph starts at 2008. So prior to 2008, the use of the archive going back to 72 was practically non-existent. It was negligible because the data came at a cost. And just before it went free and open, I think it was about $600 a scene. And you can see the exponential download rate, you know, that ensued with free and open. And we're well over 100 million downloads since then. But as I said, you know, the new model, which, you know, the panel was asked the question about what's going to happen in the next 5 years, I would predict that downloading will become more an activity of last resort, and folks will do their analysis in the cloud, especially if it's over, you know, petabytes of data. On the right, you can see in that pie chart where most of the usage is today, as you might expect, with 30 meters per pixel and 11 bands, spectral bands of data, with 8-day revisit. The sweet spots there, land use, land cover change, and ag forestry, ecosystems, disasters, and so on. So, you know, I purchased a couple of Landsat scenes, I think in 06 it was, and prior to the 2008 policy for free and open, the catchphrase was, you know, especially among academics, was they purchase, you know, they use what they can afford, right? And that's totally changed that mindset of how people interact with Landsat. And now you can literally get the entire archive and you know, do the analysis to your heart's content. By the way, even though I'm the acting director of Aeros, I paid $1,200 for a pair of scenes, and nobody's offered to reimburse me for that yet. So I don't think I'll ever see that, but that's okay. Next slide, please. So kind of a busy slide here. This is Aeros. These are the four major branches, if you will, of Aeros. Aeros originally the original intent of Aeros was to serve as the processing and distribution hub of the data. Right? Since then, it's evolved into essentially an end-to-end, you know, full-service capability. So, whether you know it or not, USGS is an aerospace agency, along with NASA and NOAA. You know, we do have a partnership with NASA, but we own and operate the Landsat missions today and do all the back-end processing and distribution. So, just kind of walking through from left to right on this, following the flow of the data, if you will. So, we're responsible for new mission development. So we interact with users to find out, you know, where their needs are going to be in the future to develop the, you know, the next generation systems. And then satellite and ground system operations, like I said, we fly the satellites. And we do all of the on-orbit maneuvering, all the downlinking, obviously, and back-end part of it, which is the data center and systems. You can see in that graphic we manage, and this number kind of, fluctuates, but maybe 75 petabytes of data today. It's not just Landsat, it's geospatial data in general. A lot of that is raster data. In fact, Landsat makes up a relatively small part of that total. But as I said earlier, the entire Landsat archive is now in the cloud. And then finally, we do the exploitation part. We have a science, and I said, notice I put in parentheses, open. All the science we do is open. The science and the algorithms are published and even provided to users. So there's the exploitation part of it. So end to end, you can see at the bottom, staffing, we have about 100 federal employees and about 600 contractors. So, 80% of the workforce is on-site contracting. And we had an FY 22 budget of about 118 million. Next slide. So data science, kind of the big thing over the last 10 years. I think it was a natural evolution of the big data movement, right? That used to be, that everybody used to talk about big data. That was kind of the obligatory thing to have in your slide deck was big data. We're seeing kind of that go away, and I think data science is now the thing to talk about. And AI is the other big thing. We heard that from the panel. There's so many different perceptions on what AI and deep learning is. I mean, there's my manager's perspective, there's Hollywood's perspective, there's my grandmother's perspective, and then there's, the reality of it. So AI is just, the term goes back, decades easily. And machine learning, so oftentimes you hear these coupled AI, ML. Machine learning goes back decades. So what's new? I mean, it's kind of a repackaging of old ideas. So deep learning is really what, more often than not, what people are talking about when they say AI. So deep learning is based on neural networks, right? Which that goes back to the 1940s. I studied in the 90s. So deep neural networks kind of went out of fashion several times throughout its history, became a four-letter word. But what turned things around, maybe about 10 years ago, was the use of GPUs, graphical processing units, to drive neural nets. That allowed us to scale out the size of these networks to become deep learning, and their ability to exceed the performance of the traditional, I'll call them, machine learning techniques, which are still in use today. They didn't go underground, but their ability to outperform those was demonstrated. So you've all been using deep learning for at least 10 years if you've got one of these. The speech recognition algorithms using these are based on deep learning neural networks. So more than anything else, deep learning and AI, if you will, and data science is about a data-driven approach to decision-making. It's driving the decisions with more data that we have. Is this the first time we've been able to do this? No. I mean, data-driven methods, again, go way back. Statistical methods, have been around forever. So to me, it's kind of a, again, not to be redundant, but kind of the next evolutionary step of big data, because what's big data? I mean, that's, everything's relative, and I think the same can be said of data science. We've always been doing data science. What's new is the volume of data, and that's going to continue to increase, and the methods by which we're inferring information from that data, which is through deep learning. These days has become, one of the premier ways to do that. Anyway, I can wax philosophical on data science and AI for a while, but that's not what this talk is about. So next slide, please. So here you see a little animation of the orbit and the collection of the data. It's 185 kilometer swath width. This is Landsat 8 and 9, how it works. It's in a nearly polar orbit, and as the Earth rotates, you get your kind of painting effect of the planet. And after about 244 orbits and every 16 days, you get the entire landmass of the Earth, covered by Landsat. So it's it's key to understand that Landsat is a global survey mission. It's not a point-and-shoot mission. So you may ask, well, every 16 days, that sounds like it's a pretty coarse sample resolution. And that's true, in a relative sense. This is from one satellite, and again, the mission is global survey. It's 30 meters a pixel. It's not going off nadir, right, to do point-and-shoot like some other application areas, especially in national security, right? Because it's important to maintain your illumination geometry for purposes of doing analysis through time. It enables the temporal dimension in ways that you can't when you're going off nadir. So Landsat is always looking straight down. That's by design to maintain the illumination geometry. Next, please. So a key part of taking advantage of that illumination geometry is consistent calibration throughout, especially radiometric calibration. So there's geometric calibration, which I think everybody understands. The radiometric part is more about the intensity signal itself. It's standardizing that through time and through different kinds of instrumentations so that you can compare observations as apples to apples and do time series analysis. So what you see, by way of example, on the left here is what's known as the top of atmosphere. This is what the sensor itself in orbit is seeing. The atmosphere hasn't been corrected for in this particular case. It's not always this dramatic. But the image on the right is an atmospherically corrected or surface reflectance. So we're mimicking, if you will, how the surface would reflect, or basically at ground level. Now, it's not perfect. There are algorithms through which to do this, and the algorithms have been published. Users are free to do that. They'd much rather have the government do the atmospheric correction and use the surface reflectance. It's become the most popular product that we offer now is the surface reflectance product. One more, please. You can see that we also identify the clouds. We offer what's called a QA band, quality assurance. It has metadata about clouds and shadows, cloud shadows, ice, snow, that kind of a thing. Again, to relieve the burden from the users from having to do all of this processing. And that's become known as analysis ready data. Next, please. Little animation here. So the purpose of analysis ready data, and various people have chosen to define what they mean by analysis ready data. It depends on what kind of analysis you're doing, what the data is. But the original definition that goes back to maybe 2017 for Landsat, and there was a pivotal paper published on the spec for what we mean by Landsat analysis ready data, 2017, is being able to stack the data through time, right, so that it is radiometrically consistent and geometrically, of course. We've retiled the product, so there's you don't have to worry about overlap when you get the old way of downloading through scenes. To facilitate time series analysis. That was a fundamental tenet of what Landsat Analysis Ready Data was supposed to support. Next, please. So here you see a little animation. This is New Cairo. This is east of Cairo, just to see, goes back to 1972, just to show how you can go back in time and visualize these changes that went through pretty quickly there. But the easiest way to visualize change through the archive is to go to Google Earth Engine. They have a free interface that anybody can click on any point on the planet, and it goes through largely Landsat data, and they've included newer data from the Sentinel spacecraft, for example. And it's pretty neat to go and just do a time-lapse visual through, and they start in the mid-'80s, which was with Landsat 4, but essentially 40 years worth of data. However, being a scientist, scientists want to quantify the change, of course. That's how we get the most value of the data. So next, please. So the way we do that, I'll give you an example in this slide here. So we're looking at a piece of a Landsat scene in the Sierra Nevada mountains of Central California. This is surface reflectance data. So that yellow arrow is pointing at one particular pixel there on the mountainside. Okay, so go ahead, click one more time. You're going to see for just this pixel, all of the observations collected from the early 80s, as you see that those observations kind of pop up on that graph below, all the way out to, I think it's going to go up to 2017. And then how we fit those observations, right, with this harmonic model, that sinusoidal shape, right? And so the first thing that's obvious for most people from that sinusoidal shape, it's showing you the seasonal change, right? Where the peaks are summer and the troughs are winter. And this is just for one band of data. This is for the shortwave infrared band. So you can see a couple of changes going on from this 32-year segment of spectral temporal, observations. If you click one more, you'll see prior to this fire event in 1988, the land cover type was tree cover. We had a fire event, that particular location. Then we had to this grass to tree conversion process go, and you can see that long-term trend. You can see the curve kind of going downwards. That was reflected in the intensity, the signal we were capturing as this downward trend. It was getting darker. And then you see another disruption in 2015 was another fire event, and the process, is likely to continue. So what's different here is we're not just classifying a pixel or pixels at one particular point in time. I think many people are aware of the supervised classification process for doing land cover classification. We're actually classifying the data as a spectral temporal piece of information. So we're classifying these time segments to a particular land cover type because there is change going on. There's seasonal change going on, right? But it's important to account for that in order to detect disturbances in long-term trends. And that's really the future of where we're going with land imaging. And so the reason it's important to be able to monitor and understand where these changes occur in time is so that we can understand why the change occurred in the first place. Once we understand that, we're in a much better position to develop models for predicting future land change. And so this method that I'm sharing here with you does this for every pixel, for every band, except for the thermal bands in Landsat, and we've created this change information for the users, for the entire U.S. Still working on Alaska. Next, please. So once you fit a math model to the observations, as we just saw, then you can throw out the observations and use the math model to essentially predict or synthesize reflectance data anywhere in time where the archive, where the images were taken. So here you see by way of example. See on the left, Landsat 7 was a June 13 collection in 2007. It was observed, and Landsat 7, some of you may know, has this scanline corrector artifact. It's got that Venetian blind effect of missing data. Seen on the right is completely synthesized. Every pixel in there is from that math model fit for all of the bands. Next, please. Same idea here with cloud coverage for this September 14, 2009 scene, and then the synthesized version. So the power of this is to be able to create a land cover map at any point in time through the archive, as you see in the bottom right. Okay. So while this is interpolated data, in effect it's temporally interpolated, there is still a significant amount of value for many users to be able to go back in time and create these kinds of land cover maps based on the synthetic data. Next, please. Here's another way to convey the change through time. Here you see it as a heat map over the continental U.S., where the brighter, yellow into the reds represent more change over 85 to 2017, that 32-year stretch that this graphic represents. And the blue and dark blue is kind of where you had less change. You certainly had change, but where you had relatively less change. And again, it's about understanding why. What was the causation? And so where you do have a lot of reds here, it's often due to various farming practices or drought or flood or fire that are the cause of change. So you see the name at the top is Land Change Monitoring, Assessment, and Projection. That's the new initiative that we've been pursuing for several years. LCMAP is the acronym there. So we've demonstrated the monitoring part, as I've pretty much shown you. The assessment is that understanding of causation of change. And then the projection is where we want to get to, right? So this is data science in action. It doesn't have to use deep learning. It doesn't have to use a certain amount of data. This is what we mean by data science as far as I'm concerned. Next, please. So a way to visualize that change, the thematic cover, or the thematic product. Here you see North Cove, Washington. You can see, this is thematic data now, right? This is land cover classes. you can see from the mid-'80s to 2015, in this case, the coastal erosion going on, right? And it's quantifiable because this is land cover pixels. These are not just intensity pixels. Next, please. And again, once we understand that causation, we're able to develop models for projecting into the future. Here you can see, and this is still, in its infancy of development, region of Lubbock, Texas here. The particular model that's being used in this scenario, this climate input, there's socioeconomic data going into this, it goes out to the year 2100, right? But what's most dramatic is that color purple, which is cotton. And because this region sits atop the Ogallala Aquifer, right, the farming community in this area has relied pretty heavily on groundwater for irrigation. Cotton is very dependent on that kind of irrigation. As the Ogallala Aquifer is depleted over time, and there's a certain model that predicts, what that rate will be, then we expect the conversion of cotton over to crops that are less dependent on being irrigated from the Ogallala. So it's this kind of scenario projection that is intended from this research, right? So imagine as a land manager, wanting to kind of look at a variety of scenarios of what may happen, how land may change within your region from a planning perspective, either to mitigate or to take advantage of potential change, right? So we're doing this on a very limited basis right now. There's certainly, all land managers, want to have this kind of a capability. And being able to project, maybe not out to the end of the century, but seasonally is really where the sweet spot is, and I think that should be the objective for our community going forward. Next, please. So this idea of change monitoring through time, right, is now being applied globally. So at the USGS Aeros, we've done it. We offer it now as a free and open product to the community. But the idea is being experimented with on a global scale by Boston University. Here you can see an example of that. You can see that yellow crosshair in South Africa, and you can see that harmonic fit model I showed you before, now for that particular pixel in South Africa. So this is available on Earth Engine Apps Experimental. It's a great platform where developers can go and experiment. Yes, it's a Google platform, but it is free and open for users to visualize and contribute, to this kind of capability. But I have no doubt that this kind of a capability is going to go global. It's only a matter of time. But of course, we're going to need the compute resources to support it, and I think we'll get there. Next, please. So here you see a linking of the LCMAP idea that I was just sharing with you with the climate side of things. This is the Lucas model, which stands for Land Use and Carbon Scenario Simulator. On the left, you see within the Mount St. Helens region, the forest cutting and regeneration process through time. This goes from the mid-'80s to about 2015. You can draw the correlation or see the correlation with carbon stocks or carbon sequestration within the trees on the right. And as the tree cutting and harvesting manifests through time on the left, you can see the carbon sequestration is highest in the yellow and lowest in the blue. You can see that go blue, right? In other words, we're losing our capacity to do carbon sequestration through forest in this case. So there's that link between land and climate. Of course, we all know that there are linkages that exist. Here's a way to demonstrate that and to try to glean information from how they're connected. Next, please. This is the kind of the new and planned imaging satellite architecture, going out for the next decade. Maybe hard to see, but that outer arc represents, years going out to 2032. You can see a number of satellite systems here being planned, and this is mainly from government agencies, both here and abroad, with the exception of one commercial. If you go next, please. You can see Landsat 9 was launched a year ago, and Landsat Next planned for the end of later in the decade. That can there's some slop in there, plus or minus, probably plus. Next, and you can see the Sentinel satellites 2C and 2D. 2A and B were already launched in the last decade, but we rely heavily on those as a to make up a virtual constellation with Landsat because they're very similar in their collection characteristics, and I'll show you that next. Here are the spectral characteristics and consideration for sensor harmonization, right? So here you see the spectral band passes for Landsat 8 and 9 across the visible, near-infrared, shortwave, and thermal, right? So this is science data. This isn't just, these aren't pictures. And this demonstrates that why it's science data, we're looking at different parts of the spectrum. It's highly calibrated data. Next, please. Here you see Sentinel-2 data, and you can see its spectral band passes and GSDs are similar to Landsat, not exactly the same. But we can take advantage of that to harmonize, right, and take advantage of multiple platforms to do our land change monitoring. Next, please. These are the hypothetical band passes for Landsat Next. You can see they look similar to Landsat 2. We've got a little more in there in terms of mid-wave and into the near-infrared, but it'll be very similar for the purposes I just mentioned. Next, please. And then finally, we have the commercial industry, mainly in the visible and near-infrared, higher spatial resolution, because that's where the market has been, right? That's probably going to change through time, although high spatial resolution is likely to be, you know, the key part of the commercial market. But being able to harmonize with that is another challenge that we're trying to pursue. Next, please. What I mean by harmonization, one more? Yeah. So harmonization, and again, it's, you know, fusion or interoperability. You've heard these kinds of terms before. But what we mean by harmonization is to harmonize at the observation level, that is at the level of signal intensity. And here you can see, you know, different bands, the red and green are colored red and green, of the different kinds of observations between, in this case, Landsat 8, the hollow squares, and Sentinel-2, the solid circles. And you can see how we're trying to do an apples-to-apples usage of all this data so we can map these or fit these math functions to these observations in a way that I described before. So the goal is to leverage more observations out there through harmonization to do a better job, more accurate job, more rigorous job of fitting math models. Next. So we're seeing one more please. We're seeing more shared space here between what was traditionally national security applications versus federal civil, especially in regards to climate change. Yes, we can say that these days. And the environmental sciences, may be different with the next administration, who knows. But geospatial data science is really where there's a tremendous amount of new shared space between what national security didn't focus as much on and are now seeing it as a national security interest or concern. And so we're taking advantage of opportunities there. One more slide. This is my last slide. Community priorities as I see it for open land imaging going forward. So I talked about the need for analysis-ready data to facilitate time series analysis, right? So we can understand, detect first, understand the causation of change, so we're better able to model future scenarios of land change, and that, at the end of the day, is what land managers want most. Methodologies for harmonizing Earth observations. I just shared with you what harmonization is about. We've demonstrated that with Landsat and Sentinel. There are many more systems and platforms that will be flying in the near future throughout the remainder of this decade that we need to take advantage of through harmonization so we can collectively harness government data. And the last bullet is to get to that, ability to forecast land change to inform decision making, right? It's all about the protection of life, property, which is, what the mission of the Department of Interior is and our cultural heritage, as are many other government agencies. So at the end of the day, that's what it's all about. Thank you very much.
Thank you. Well, we do have a question for you, if you'd like to.
Sure.
So this question we've got here actually might be a good question for a completely separate panel. Yes. So anyway, the question here is, there are a lot of duplication across agencies for geoportals, including the GeoPlatform, which will be discussed later today. How do you see centralized geoportal for the federal government developing, or will this continue to be somewhat decentralized?
That's actually a great question for David in his role. So, that's a good point. Some folks have suggested, in terms of consolidation and, be more efficient through the economies of scale. The same thing with the way we distribute satellite data. For example, we've got the 3 major federal civil agencies, NASA, NOAA, and USGS. It's been suggested, why can't we just combine that? So I think, to a certain extent, it's kind of the way our system of governance does work. I think it does promote a certain level of competition among government agencies in a healthy way. So in Europe, for example, it's somewhat different. It is more socialistic, and you do see more of these grand unified types of architectures in Europe. But it's a fair question. I'm not sure, to be honest with you, that that's the optimal way to do it. You would gain economies of scale, but there are other issues that have to do more with, again, just the nature of the way government operates. Todd, or David, I don't know if you want to add to that. But
No, there's so much that we could talk about on this that I think this would be a good panel discussion maybe for next year.